Ну что ж, давайте мы будем начинать нашу сегодняшнюю публичную лекцию. Сегодня у нас в гостях сэр Кристофер Llewellyn Смит. Значит, разрешите мне сказать несколько слов о его биографии. Вообще, Крис по своей, так сказать, научной специальности занимается физикой элементарных частиц, физикой высоких энергий. Он автор многочисленных работ в этой области, старших классическими работами. Это работы в области физики сильных взаимодействий, физики кварков, физики взаимодействия нейтрино с кварками. Есть многочисленные, хорошо известные работы и в области рассеяния частиц при высоких энергиях. Есть понятие в физике высоких энергий, которое названо имена, это носит имя Llewellyn Смит, например, правило Субгросса Llewellyn Смита. Вот это его область, так сказать, научных интересов до последнего времени была. Вообще-то он закончил, он получил степень PhD в Оксфорде в 1967 году. Надо сказать, что первым местом работы Кристофера Llewellyn Смита был ФИАН. Он здесь поработал, хотя и не очень долго, но продуктивно. Затем он был постдоком в ЦЕРНе, работал в СЛАКе, Стэнфордском центре, в Стэнфорде, в Соединенных Штатах. Возвратился в Оксфорд в 1974 году. И с 1987 года по 1992 год он был председателем физики в Оксфорде, chairman of Oxford Physics. И уже тогда его организационные способности проявились. Он объединил 5 тогда факультетов, которые занимались физикой, единый мощный факультет. Сейчас это один из самых сильных факультетов по физике в мире. С 1994 по 1998 год он был генеральным директором ЦЕРН. И в то время, надо сказать, в ЦЕРНе, ну и сейчас тоже, конечно, но тогда оно было очень интересным. Тогда работал электрон-позитронный ускоритель ЛЭБ, самая мощная по тем временам машина и очень информативная машина. В это время, как раз когда он был генеральным директором и под его, соответственно, руководством происходила модернизация этого ускорителя. А в 1994 году, как раз в то время, когда он был директором генеральным ЦЕРНа, было принято окончательное решение о строительстве Большого адронного коллайдера, той машины, о которой мы все хорошо знаем, наслышаны, и которая будет строить сейчас в ЦЕРНе. Значит, с 1999 по 2002 год он был президентом University College в Лондоне, а сейчас он председатель консультативного комитета Euratom по термоядерному синтезу, а с 2007 года председатель совета ITER. Значит, и директор отделения, Пулханского отделения, значит, совета или агентства Соединенного Королевства по атомной энергии. И это отделение отвечает как раз за термоядерную программу и работу Токамака, который там существует, называемого Объединенный Европейский ТОР. Значит, ну, кто такой Токамак, это вы, наверное, еще услышите. Но, во всяком случае, в последнее время он занимается термоядерным синтезом, исследованием по термоядерному синтезу. В 1999 году Крис получил медаль и премию имени Вейсбрука Института физики британского. С 1984 года он член Королевского общества, аналог Академии наук Великобритании. Ну и в 2001 году он был, как сказать, посвящен в рыцарское звание. Теперь он, значит, сэр Кристофер Llewellyn Смит. Так что вот такая богатая биография, очень интересный человек. Мы все, конечно, приветствуем его и рады выслушать эту лекцию.
Спасибо большое. Уважаемые товарищи, я очень рад возможность выступить именно здесь, в Фиане, с докладом о проблемах ядерного синтеза. Для этого есть две причины. Во-первых, 41 год назад я сам работал здесь, в Фиане. Хотя последнее я часто бывал в Москве, сегодня я впервые вернулся в Фиан после долгих лет разлук. Я очень этому рад. Во-вторых, хотя знаменитый Tokamak самое перспективное устройство для термоядерного синтеза был построен в Курчатовском институте под руководством Льва Андреевича Артемовича, изобретен и разработан Tokamak был здесь, в Фиане. Это сделали знаменитый советский физик Игорь Евгеньевич Там и Андрей Дмитриевич Sakharov. I will now continue in English.
So, as I was implying, the father of modern fusion research was Lev Andreevich Artemovich. In reply to the question, when will fusion be ready, Lev Andreevich replied, термоядерная энергия будет получена тогда, когда она станет необходима человечеству. Fusion will be ready when society needs it. I want to address the questions, why is fusion needed? When will it be needed? When will it be ready? Was Lev Andreevich correct in saying that it will be ready when society needs it? So the need for fusion is related to the meeting the challenge of supplying enough energy for the world in the future. We use a great deal of energy. The rate at which we are using energy is 15.7 terawatts. It's a very large number, difficult to understand. If you divide by the population of the world, you find that we are using 2.4 kilowatts per person. In other words, we are using energy at the same rate as burning 24 100-watt light bulbs continuously for every man, woman, or child on the planet. We are using this energy extremely unevenly. For each person in the United States, 50 times as much energy is used as in Bangladesh. In the Russian Federation, United Kingdom, we are somehow in the middle. According to the International Energy Agency, world energy use is expected to increase by nearly 50% by 2030. It's not clear where that energy can come from. In the developed world, I certainly in the United Kingdom, could use less energy while maintaining our standard of living. But we have to remember that there is still 1/4 of the world's population, more than 1/4 of the world's population, has no electricity. These people in the developing world need more energy to achieve anything like what we would consider to be a decent standard of living. So although we can use less energy and should and must use less energy, there really should be an increase in the developing world. And as a result of this, it is likely that energy use will go up. Where is our energy coming from? 80% of the world's primary energy is generated by burning fossil fuels, oil, coal, and gas. This is causing potentially catastrophic climate change, and it cannot be sustained in the long term because oil, coal, and gas will not last forever. I want to consider the timescales for action to avoid climate change and to prepare for the end of fossil fuels, and to discuss what actions we should take, which include, of course, developing fusion. Let me start with the time for the end of fossil fuels. There is a saying in Saudi Arabia. My father rode a camel, verblud. I happen to know this word in Russian. I drive a car. My son flies a plane. His son will ride a camel. Is this true? Very likely, yes. Oil will be largely finished in 50 years, perhaps much sooner. Many people think we are already reaching the peak of world oil production. Even if you take the most optimistic estimate of the amount of oil that remains to be discovered and to be extracted from the ground, that's the estimate of the US Geological Survey, the peak of oil production cannot be more than 20 years away, and then oil production will decline. So you see on my picture here, the sun is setting on the age of oil. Gas. Gas will last a little bit longer. What about coal? It's often said there's plenty of coal, enough for 200 years. But you must read carefully. The next line says enough for, well, it says enough for 200 years at the current rate of use. But the use of coal is going up 4.5% a year. And when oil vanishes, coal will be used even more. With an increase of 4.5% a year, a supply for 200 years turns into 50 years. So we need to start preparing now for the era when there are no longer any fossil fuels, oil, coal, and gas. What about climate change? What's the time scale? Carbon dioxide stays in the atmosphere for hundreds of years, maybe up to 1,000 years. So we should have taken action already many years ago, which we did not. In my opinion, it's likely that most of the remaining fossil fuels will be burned in 100 years. It's very difficult for me to imagine that the world will say, no, we stop using fossil fuels. It's cheaper than any other way of getting energy. And anyway, as we will see, we do not have other ways of producing so much energy at the moment. If this is correct, the only action that can help us with climate change is to capture the carbon dioxide coming from power stations and bury it underground. This is a technology which has been used on a small scale, but it's not developed sufficiently to be confident that it can be used on a very large scale. However, I'm sure that we must develop it, and if it turns out to be practical, I expect that it will turn out to be practical, it should be used on the largest scale possible. This is very, very easy for me to say, but it will put up the cost of energy, so it's harder to imagine that it will actually happen. What should we be doing to prepare for the end of the fossil fuels? We should be reducing in the developed world our use of energy. And there are some, what I call low-hanging fruits, the fruit you can take easily, the things that are easy to do. There are huge gains to be made in road transport, for example, in buildings. 50% of the world's energy goes in operating, heating, lighting buildings. And if we do these things, we can actually save money. Nevertheless, we are not doing them. But although by being more efficient in using energy, which we must do, we can reduce the growth in the use of the world's use of energy, I very much doubt that we can actually make the amount go down, unless we are prepared to see a very big difference in standard of living in Africa and India and so on, and the standard of living that we have, and even to see that increasing. But we must reduce energy as much as we can. The second thing we must do is develop and expand low-carbon sources of energy. Where does our energy come from today? 80% comes from burning fossil fuels, oil, coal, gas. Burning waste and wood and rubbish is 10%. Much of this is in principle renewable, but very, very little is being renewed. Nuclear, it's about 5%. Hydro, this is the so-called thermal equivalent of hydro for the experts, about 5%. And the rest, wind, solar, geothermal energy, tidal energy, wave energy, 0.5%. These are rounded numbers. So if the 80% is gone, it's going to be very difficult to replace them. And you see, if you want to replace with wind, solar, geo 80%, you need to increase these a factor of 160. That's a tremendous challenge. What can replace the 13 terawatts that we're currently getting from fossil fuels? 13 terawatts, which is growing. Could it be wind? No, there's not enough. So I've tried to work out here the maximum potential of this, again, thermal equivalent for the expert, of what we could get. From wind, optimistically, maybe 3 terawatts. From geothermal, 100 gigawatts. Hydro, we're already getting a lot. We could get another 1 terawatt. Bioenergy, maybe another 1 terawatt. Marine energy, tides, etc., maybe 100 gigawatts. You add these numbers, they are less than 6 terawatts. But we are trying to replace 13 terawatts, which is growing. So there is a big gap. But of course, we must use the wind, geothermal, hydro, marine, bio to the maximum extent possible. Though again, this is easy to say, but not so easy to do. As long as there are fossil fuels, it is cheaper to burn fossil fuels, but we must do it. But still, 6 is less than 13. There is a big gap. So we have to look for something else. What could that something else be? The only other options are solar and nuclear, fission or fusion. There is a lot of solar energy hitting the Earth. If you took 1/2 of 1% of the Earth's land surface, this is still a big area, by the way, 1/2 of 1%, and turned the energy from sunlight into, say, electricity with 15% efficiency, you would get 19 terawatts. And that's electricity, so that's equivalent to 50 terawatts of primary energy. So this is plenty to power the world. But it's very expensive. The sun is not shining in Moscow at 5 o'clock in the evening in January. So if you want to use solar energy, you need means of storing energy or transmitting it. So if we want to use solar energy, we need big breakthroughs in cost, in transmission, and in storage. But in principle, solar can meet our needs, so we must develop it. What about nuclear? Nuclear fission, we have today. However, nuclear fission is just burning uranium. And the cheaper uranium is going to be exhausted at some date, be finished. I will show you some figures. When that happens, we will need thorium reactors, which are harder, or fast breeder reactors, which use the uranium more efficiently. And the only other option is fusion. So we have very few options. We must develop all of them. I'd like to just say a brief word about solar and fission. So solar, there are 2 ways of dealing with solar energy. You can use photovoltaics, turn sunlight directly into electricity. It's expensive. Probably but it's already in use in certain uses. Solar concentrated, also already in use, may be more promising on a large scale. This is a system where you take troughs which focus the sun and make heat, and they heat up salts which they melt. Or you can make, as shown on the right, you can make mirrors that concentrate the sunlight at the top of a tower where you can reach very high temperature. This then, the heat is used to drive turbines, and the salt can store the heat for several hours after the sun is no longer shining. So this has some advantages. Also, you can get to high enough temperatures that there are processes involving compounds of sulfur where you can take heat and water and make hydrogen, which is a method of storage. So this is a technology that must be developed, but to get to the very high temperatures, we'll need new materials. And if you go to very high temperatures, there is a problem of the fatigue from the daytime temperature to the nighttime temperature. But this must be developed. What about uranium and fission? So the uranium is in 2 categories. The bottom set here, the darker color, the conventional resources, the sort of uranium which is being taken out of the ground today. And the estimates are that there is somewhere between 3 and 16 million tons remaining. Then there are unconventional resources at the top, but there's at least 200 million tons. These consist of uranium in sandstone, in seawater, and in phosphates. Huge amounts, but extremely expensive to get out. Too expensive to extract this uranium at the top of the slide to use in conventional nuclear reactors. So for conventional nuclear reactors, we are stuck with this at the bottom of the slide. If we take the present use of uranium and extrapolate the line here, there's enough for about 200 years. But that is with no growth. And already today, you see around the world, there is a restart of the nuclear age. More people are building nuclear reactors. When you put in some growth, let's say 1.8%, you run out towards the end of the century. You run out with the biggest estimate. With the smallest estimate, we run out much sooner. So if we want to use fission, which we must, in my opinion, we need now to be developing thorium reactors and fast breeder reactors, which use uranium more efficiently and possibly could make it economical to use the unconventional uranium resources. So let me summarize now on the energy challenge and the need for fusion energy. In my opinion, the only way I cannot believe we will not use the rest of the oil, coal, gas. So if we are serious about avoiding climate change, the only option is to capture and put underground the carbon dioxide, if it can be done. In anticipation, looking forward to the end of fossil fuels, we must use energy more efficiently, and there are big gains to be made. We must expand wind, geothermal, hydro, bio, marine power to the maximum extent that's sensible. But this will still leave a huge gap. And in about 50 years from now, we are going to be staring at a gap of 7, 8, 9, I don't know how many terawatts, which can only be filled by solar, fission, which in the long run means thorium and fast breeders, which will be more expensive, or fusion. So there are not many options. And we must develop all as a matter of urgency, including fusion, although success is not 100% certain. So let me come now to fusion. First thing is that we know that fusion works. It powers the sun. Without fusion, we would not be here, and all the stars. Controlled magnetic confinement fusion experiment, the Joint European Torus, which is the biggest in the world, you see it here with a person on the right to set the scale, has produced 16 million watts of fusion power. It took slightly more to operate the device, and this was only for a second or so. But this at least shows that we can make fusion work on Earth. So we know it works. The big question is, when will it work reliably, economically, on the scale of a power station, which has to be bigger than this, as I will explain. But before I answer that big question, I want to discuss what is fusion, and you will see it's very complicated. If it's so complicated, why should we bother? And why is it taking so long? So what is fusion? The most effective fusion process involves deuterium, heavy hydrogen, and tritium, super heavy hydrogen, heated above 100 million degrees, maybe 150 million. 100 million degrees is 10 times hotter than the core of the sun. So deuterium consists of one proton in green and one neutron in blue. So it's electrically like a proton. So it has one electron going around it, and chemically it's like hydrogen. It's just twice as heavy because there's also a neutron. Tritium has one proton and two neutrons, so it's 3 times as heavy. Chemically like hydrogen, super heavy hydrogen. So if we heat them to 100 million degrees, they can fuse. I will explain in a minute why we need such high temperature, and rearrange the nuclei into helium and a neutron with a huge amount of energy. This energy in the form of kinetic energy, energy of motion. And it's shared inversely proportional to the mass. The neutron has 14 million electron volts, helium 3.5 million electron volts. Now, I won't explain what an electron volt is, if there are people who don't know. I will just say that fusion produces more than 10 million electron volts. A chemical reaction typically produces 1 electron volt. This means that in fusion you need 10 million times less fuel than in a fossil fuel reaction. So as written on the bottom of the slide, if you have a 1 gigawatt, a 1 billion watt coal power station, it uses 10,000 tons of coal a day. For fusion, to produce 1 gigawatt, you can divide by 10 million. So you need 1 kilogram of deuterium and tritium. So this sounds quite interesting, except that I haven't told you yet where to get the deuterium and tritium. When you have this hot gas, you must keep it away from the wall. It's very, very dilute, maybe 1/1,000,000th of atmospheric density. If it touches the wall, it will be cooled down, and it will damage the wall. So how can we keep the hot gas away from the wall? The answer is these particles are electrically charged, so they are guided by magnetic fields. And the answer is to use a device called a Tokamak. So the Tokamak stands for Torodolnia Kamera s magnetnymi katushkami, and was invented by 2 physicists from FIAN, as I already said, Igor Yevgenovich Tam and Andrei Dmitrievich Sakharov. So here's Sakharov, I think at the age of 22 in 1943, and a somewhat more mature Tam sitting here. Now I'd like to explain why you need this very high temperature. If you take a gas of deuterium and tritium, the molecules, atoms are moving around. As you heat it up, you put in heat, they move faster and faster. And at a few thousand degrees centigrade, the collisions between the atoms knock off the electrons. And you find a new state of matter called a plasma, in which consists of the nuclei of deuterium, the nuclei of tritium, and the electrons, separated. So it's a mixture of electrons and nuclei. As you heat it, the nuclei can approach each other, but normally they just bounce off each other because there's a repulsion of the electric charge. But as you make it hotter and hotter, they go faster and faster until eventually, above 100 million degrees, they come close enough that one can grab the other with a nuclear force and fusion can occur. So I've given a picture of this here. So this is a bouncing collision. Just one bounces off the electric charge of the other. But at high enough temperature, when they're moving fast enough, they can fuse, like that. Now, this is all slowed down, of course. I show it again, still slowed down, but with the relative velocities correct. So this is the bouncing collision. They just repelled by the electric charge. And now, with the relative velocity correct, when they can come close enough at high temperature to fuse, like that. So a huge amount of energy is produced. So what are the challenges? The first challenge is to make an effective magnetic bottle, a tokamak. In some sense, this is done. In the joint European torus, we can produce conditions which would be okay to make some sort of power station. But you would like to get to higher pressure. Higher pressure means more density. Higher density means more fusion. So most fusion research is concentrated on pushing up the pressure. But if you push the pressure too high, the gas becomes unstable and will come out of the magnetic bottle. So most of fusion research of the plasma is looking at the plasma, trying to find out how to control or avoid the instabilities. The second challenge is to make a strong container, because the neutrons, in a way I will describe in a minute, come out of the gas into the wall. So the wall is being bombarded by a very large flux of energetic neutrons. We have to find materials which will stand up to the neutron bombardment. It's a very big problem. And finally, we have to make the system reliable. Fusion is very complex. I personally think we can make a fusion power station of some sort. What I'm not so sure is, can we make one which will operate 70, 80% of the time? Probably we could make one that operates 5% of the time, but that's no good. And the complexity is going to be perhaps the biggest challenge of all. So what would a fusion power station look like? So at the center in this torus, there is a volume of deuterium and tritium plasma, maybe 2,000 cubic meters, big volume, heated in a way I'm not going to describe, to 150 million degrees. And this we can do every day in JET, in the UK, and other fusion devices. We reach such temperatures. Deuterium and tritium is fed in. At this temperature, the deuterium and tritium fuse. The helium is captured in the magnetic bottle because it is charged. But the neutrons come out into the wall, and they are stopped in maybe 50 centimeters. So surrounding the plasma, there is a blanket. It's about this thick, a meter thick, something like that. The neutrons are stopped in the blanket. And two things happen. They are slowed down, so they heat up the blanket. And the heat is taken out through a cooling circuit, which is then used in a secondary circuit to boil water and drive a generator. So this is a fusion power station is like any power station that works by making heat, like a coal power station, like a fission power station. It makes heat, it boils water, drives turbines. But it has a different fuel and a different furnace in the center. The other thing the neutrons do is they react with lithium implanted in the blanket to make tritium, the fuel of the reactor. Because tritium is unstable. It only lasts 12 years. It's not available naturally. So we have to make tritium. We have a certain amount of tritium. You can make it in fission reactors. We have enough tritium to start the first power plant. But then to keep it going, the power plant must make its own lithium. So this is, you don't see it here, but it's actually quite complicated. It needs very sophisticated vacuum system, very sophisticated magnets, heating system, and so on. So if it's so complicated, why bother? And the reason is given here. Lithium is extremely abundant. It's in seawater at 100 times the concentration of uranium. And you can definitely get it out cheap enough for the purposes of fusion. And before that, there's plenty in the land before we go to the sea. And we need a tiny amount of lithium. I have done the following calculation. Well, first let me remind you why you need lithium. So you see at the top here, the lithium is used to make tritium. And the reaction is that a neutron coming into the wall finds lithium in some form, and there's a reaction, a neutron hits lithium and makes tritium and helium. So you have a little bit of tritium to get going, and then the reactor makes its own tritium. And as the neutrons slow down, one neutron can make two neutrons, can make three neutrons, etc. You can make plenty of tritium. In principle, it hasn't been tested yet. So now we can ask, so the raw fuels are lithium, from which we make tritium, and water, from which we extract deuterium. So left over from the Big Bang at the beginning of the universe, 1 in every 6,700 hydrogen atoms is actually a deuterium atom. So there's plenty of deuterium. And we can extract it very, very cheaply at a negligible cost, effectively. So there is enough lithium and water to power the world with fusion for millions of years. And we need a tiny amount. So I have done the calculation of how much energy could you get from the lithium in the battery of one laptop. And the answer is, along with the lithium in one laptop battery, you would need 40 liters of water to get deuterium. And with this, you could produce 200,000 kilowatt hours. That is a lot of electricity. It's for the European Union, that is the total amount of electricity produced divided by the population for 30 years. So this one lithium laptop battery will provide not only my personal needs, but my share of the use by industry and so on for 30 years in an intrinsically safe manner with no carbon dioxide. So in my opinion, these numbers, by the way, to produce the same amount of electricity, you need 70 tons of coal. This is enough reason to develop fusion until or unless we find a barrier. So the advantages of fusion are pretty clear. The disadvantages, we don't have it yet, and most of my talk will be on what are the problems, how long will it take. Unlimited fuel, not literally, but 1 million years, it's enough for me. No carbon dioxide or air pollution. Intrinsically safe. Fusion has to be continuously fueled. It just stops. If anything goes wrong, it stops. There's no possibility of a runaway reaction. The most dangerous thing is the tritium, but there are tiny amounts. There's this very big volume, but it is about 1/1,000,000th of the density of the atmosphere. So there's only the weight of a few postage stamps of tritium in a fusion reactor. And if it escaped, you would not have to evacuate people nearby. And it's rather easy to prevent it escaping. Fusion directly produces no radioactive material. However, it is true, and this is in the disadvantages, that in the wall, the neutron can make radioactive material, but we can choose the wall material such that that radioactive material has a short half-life. Probably the competitive price can be, the electricity cost could be competitive, at least compared to other carbon-free electricity sources, such as wind or even fast breeders, if we can get it to work reasonably reliably. So those are the advantages. If we had this, it would be wonderful. What are the disadvantages? The blankets do become radioactive, but we can choose the materials such that the half-life of the radioactive materials is 10 years. All components could be recycled to a new fusion power plant in about 100 years. So it's a problem, it's radioactive, but it's not a problem for 1,000 years, for 10,000 years, for 100,000 years, which it is for fission. Not that I'm against fission. The second problem is we need more research and development. So why is it taking so long? Why is it so difficult? There are 3 reasons. The first is that we cannot demonstrate fusion on a small scale. If I wanted to convince you of coal power, say in the 19th century, I was looking for investors to make a coal power station. I could make a coal power station this size, and you would be convinced we could make electricity with a little dynamo. But fusion, the power you get out of a fusion device divided by the power you need to make it work increases faster than the square of the dimensions. I will explain why in a minute. So you can only demonstrate fusion on a very large scale, costing billions of dollars. Otherwise, we would have just tried. So progress has been quite slow and cautious. You cannot convince the government to spend $1 billion until they're almost sure it will work. So instead of just saying, let's try, maybe it works, maybe not, you wait until you're confident. Second reason is fusion has not been funded with any urgency. The basic geometry was already developed by Tam and Sakharov in the 50s, and by the late 60s it became clear to the world that Tokamak was the right device. We could have been from 1969, when the rest of the world paid attention to the Tokamak, we could be where we are today 15 years ago if there'd been more urgency. But in the 1980s, what's the problem? No one's worrying about climate change. There's plenty of coal. Why bother? And finally, it is technically very difficult. You have to heat 2,000 cubic meters of gas to 10 times hotter than the center of the sun, keeping it away from the wall. You have to find the strong materials for the walls, and you have to ensure the reliability. Nevertheless, although we could have done faster, the progress has been enormous. And I want to show you the progress from the Russian Tokamak, Tokamak number 3, which convinced the world that Tokamaks were the right device, to jet and then to ITER. So here on one slide is T3, which you can't even see because there's stuff outside it. It had a volume of about 1 cubic meter of plasma. Temperature reached 3 million degrees, but that was enough to excite people. This established, the rest of the world started to believe this in 1969. Already within 3 years, people were designing jet. This is a huge step, very daring. And jet is 100 cubic meters, temperature of 150 million degrees, world record for fusion power. But it's still not large enough. We need something at least twice as big in every dimension. That's called ITER. So there has been huge progress. This is the one graph I'm going to show and explain a little bit of the science. So this graph shows the things you need for fusion. Along the bottom, the temperature, and I'll tell you up the side in a minute. And these points here are results from different tokamaks around the world, beginning with T3 in the bottom left-hand corner. And as time has gone on, we've moved up from the bottom left-hand corner to where we are today. So we've come from 3 million degrees with T3 up to 150 million degrees with many devices. So the temperature we've reached. What are the other parameters that we need? First of all, we need high pressure. At fixed temperature, if you double the pressure, you double the density. If you double the density, twice as much deuterium, twice as much tritium, 4 times as much fusion. So you need a big pressure, P. And secondly, you need a very good insulation from holding with the magnetic bottle, holding the plasma away from the wall. You must be that you keep the energy in. If it flows out too fast, you will have to put more energy back than you generate. So this is technically known as the energy confinement time, Tor sub E, which is the energy in the plasma divided by the power supplied to keep it hot. If it was a perfect insulator, this would be infinite. You could heat the plasma, go away for a week, it would still be hot. But it is radiating. There are fast particles escaping. It's leaking out the whole time. So we have to put it back. But we want it as long as possible, so we don't have to put back too much. And it turns out that the thing that matters is the product of the pressure and the energy confinement time. So in 1968, 69, we were right down at the bottom. And it has increased by a factor of about 10,000. To make a power station, we need to get to about 10. And today we're at about 1 or 2 perhaps. But this we can do simply by increasing the size. And this is rather easy to understand. If I go from jet to the next device, ITER, it is twice as big in every dimension. So the volume is 2 times 2 times 2. The volume is 8 times as big. So ITER will contain 8 times as much, ITER will contain 8 times as much energy as jet. But the surface area is only 4 times as big. So immediately you gain a factor of 2 in terms of stored energy and the area from which the energy can leak out. But in fact, it's better than that, because in ITER, the heat has to travel to the wall, on average, twice as far. So in ITER, simply by doubling the size, we will move up a factor of 4 on this vertical scale. And in fact, it's better than that, because in ITER we can have stronger magnetic field, a bigger current flowing through the plasma, which makes part of the magnetic field. So we are rather confident that ITER will be in the region indicated here, which is the right region for a power station. It won't be, a real power station would have to be bigger to be economical, but we're getting to fusion power station conditions. So what are the next steps for fusion? They're to construct ITER, the International Tokamak Experimental Reactor, nowadays usually just called ITER, meaning the way in Latin, the way to fusion. It will produce 10 times as much energy out as has to be put into the plasma and have a really burning plasma. And during construction, there's a lot that we can do to prepare for ITER. In parallel with this, we need to work harder on the materials, the structural materials which will hold ITER power stations together, and the plasma-facing components that see the plasma. And this will need a special test facility called the International Fusion Materials Irradiation Facility. Europe and Japan are investing a lot of money, 150 million euros, in designing the International Fusion Materials Irradiation Facility. And we need to work on fusion technologies, remote handling, how to handle with tools radioactive materials, heating systems, the system that takes out the heat, the blanket, the fuel cycle, the magnets. So here we see on the same scale going from jet to ITER, and here's a person in front of ITER. In fact, it's more complicated than that. Also jet. On the outside, there are stuck heating systems, huge systems that are pumping the heat in to heat the plasma, and there are experimental devices. So the ITER, the aim is to demonstrate integrated physics and engineering on the scale of a power station. The key ITER technologies have been fabricated and tested by industry, and construction is beginning at Cadarache in the south of France. It's going to cost over 5 billion euros. But this is small on the scale of the problem of energy. The partners in ITER are China, the European Union, the Russian Federation, Japan, the United States, Korea, and India. These countries together are the home to over half the population of the world. So this is a global response to a global problem. In many ways, ITER is about systems integration. Almost everything in ITER has been used before, but never all together and never on this scale. So, for example, in JET, today the biggest fusion device, the magnets are made of copper. So they get hot. You can't run them for more than a minute. That's no good for a power station. A power station must run continuously. So a power station will need superconducting magnets. There are superconducting tokamaks in the world, but they are relatively small. So they've never even been used on the size of JET, let alone on the size of ITER. So ITER will have superconducting magnets. And almost every technology in ITER has been used somewhere, but never altogether at the same time and never on this scale. The only thing that really will be new is in the second phase of ITER to put test modules of the blanket to test getting out the heat, generating the tritium. So although this is really about engineering and systems integration, there are some plasma physics issues. Let me just mention that actually the news has been quite good in plasma physics in the last 20 years. There are potential problems, but there are opportunities to improve things. First, in the Tokamak, it's basically a solenoid bent into a circle. Produces a magnetic field running around like that. That's not good enough. That's what Tam and Sakharov understood. You actually need a field that goes helically like this. To generate such a field, you also have to drive a very large electric current through the plasma. 15 million amps in ITER. This takes power. But my colleagues in the UK, actually in the early 80s, predicted that in certain conditions there could be a self-generated current, so-called bootstrap current. That was discovered not until the middle 80s. Now we think we know how to use it. We think that 80% of the 15 million amp current can be self-generated. In addition, there was a discovery made by colleagues in Germany how to get higher pressure and more fusion power. I just show you a picture of that from a device in the UK. Until the early 80s, the top picture was this is a picture of a hot plasma in what's called a spherical tokamak. And the plasma density was falling off smoothly to the edge. It was sort of fuzzy, leaking energy and so on. And our friends in Germany found a way to get a very sharp edge. And you can just see it in this picture. And you can get higher pressure with less leakage. So these are big positive developments. There are possible problems. Maybe in a burning plasma at ITER, there could be new instabilities. We can imagine what they might be, but we think they won't be there. But we need to show that. Pretty confident they won't be there, but we need to demonstrate it. Can we really keep it running with the bootstrap current indefinitely? If not, maybe we have to have power stations which operate for 8 hours and then start again, or maybe something else called a stellarator. But there are potential improvements. As I said, getting to higher pressure. Every year we manage to find ways of getting higher pressure in the plasma. What about the materials problems? The problem is we have 2 megawatts, 2 million watts per square meter of 14 MeV neutrons flooding continuously every day, every night, every month, every year into the wall. Something like this is seen in fast breeder reactors, except the energy of the neutrons is typically 1 million electron volt. So this makes new problems. And the pieces that actually see the plasma-facing materials, have an additional 500,000 megawatts of hot particles, electromagnetic radiation. The theorists think they know the right materials. I'm a theorist, and I can tell you, you should not believe the theorist. Well, not entirely. We need to test it. So we need to keep developing materials, and we need experiments. So we need the International Fusion Materials Irradiation Facility. And the results from this will be needed before we can build a prototype commercial fusion reactor. Just to say the same thing on materials, there have been developments, there are potential problems, there are potential improvements. Until the early 90s, it was thought that very exotic materials will be needed, maybe silicon carbide composites in the wall. But then it was discovered in fission reactors, actually from data from the Russian Federation, that body-centered cubic low activation steels, special steels, can do the job. This is good news. There are potential problems. It's not just the neutrons of damaging the material just by the impact. These high-energy neutrons can generate helium in the walls. If they get into bubbles, they can cause the material to swell or even break. And there is a huge heat load, which we think maybe we know how to solve, but it's not really solved, on the so-called diverter. This is the device through which the helium and the impurities are taken out of the plasma. But there are potential improvements. If we can get silicon carbide ceramics to work, then we can go to much higher temperature. And with much higher temperature, we can make much more efficient fusion reactors, which will make energy at a much lower cost. So I want to come finally to how much longer this is going to take. So let me begin by talking about studies of power plants, which define what we eventually wish to build, so that we, all the time, although it's some way away in time, we are thinking about what will a power station look like in order to identify the problems for research and development. So there have been many studies of power plants, and the most recent, which was finished about 4 years ago, was the European power plant study. And these results, as far as you can do it on paper, confirm the good safety and environmental features of fusion. And they give encouraging ranges for the expected cost of fusion-generated electricity. In these studies, they looked at 4 models. So these people have a lot of imagination. They call the models A, B, C, and D. So model A is a very primitive model. You can almost build it today. It doesn't go much beyond ITER. It uses steels that we know and so on. Model D assumes big improvements in plasma performance, in materials, in temperature. Probably we will build something in between. Now, Model A, the estimate, which you have to not take too seriously, for this water-cooled early model was something like 9 euro cents a kilowatt hour. That's sort of comparable to wind energy, maybe cheaper. And that's for an early model. If you build many, cost comes down. The more advanced models, which work at higher temperature, maybe 5 euro cents. Now, you should not take these numbers seriously. We haven't done it yet. You should never believe people about future technologies. But the important point is these numbers are a reasonable order of magnitude. If it was $9 or 9 euros, forget about it. But it's not. It is coming out of the right order of magnitude. By the way, the economics of fusion favors large fusion power plants for exactly the reason that I said. The bigger it is, the more efficient. So all these results were based on power plants producing 1.5 gigawatts, 1.5 billion watts of electrical output. It would be nice to go bigger, but the people who operate the electricity systems don't like very big power stations, because if they fail, they have to bring some replacement very quickly. Nevertheless, the power station that's being built in Helsinki right now is 1.6 gigawatts. So there's nothing magic about the 1.5. If we could build a 3 gigawatt fusion power station, these costs would go down 20 or 30%. But this is for 1.5 gigawatts. But because of that, the economics means that fusion will power large centers of population. But that's okay. Half the world's population today, over half, lives in big cities or big urban areas, and that percentage is increasing. So fusion will be for these areas, not for the middle of Australia. But in those areas, Australia particularly, there's plenty of sun, and the renewables may be more sensible anyway. It's very capital intensive. It costs a lot of money, but it's very low operating cost. By the way, the uncertainties in these costs, the two biggest factors in the uncertainty are first, the availability. This assumes we can make it work 75% of the time. That's very, very difficult. That's the first big uncertainty. The other big uncertainty is capital, the cost of borrowing money. But if you've built it, it's very cheap to operate. So there's lots of off-peak electricity. You could make hydrogen, perhaps. Now, that's what we want to build, and these results we fed into a study we made of how long it would take. The study was quite long and technical, but the results are easy to understand. So we looked at what is called the fast track. It's very slow, unfortunately, but let me tell you the idea. In the past, people had the idea, let's build ITER. Let's see if it works. If it works, then afterwards we start worrying about materials and technology for a power station. The fast track says that's a bad idea because it will take longer. And anyway, we're rather confident that ITER will work. So in parallel with building ITER, we should work on the materials and the technology. And this philosophy was adopted about 5 years ago in Europe. It's still very slow, as we'll see. So this is the timetable, assuming there's enough money. If there's not enough money, it's not like this. And we don't get any big negative shocks. So it will take about 10 years to build ITER. Then to operate and gain sufficient experience from ITER before you will be prepared to build a real power station, maybe another 10 years. In those 20 years of building ITER and operating ITER, we assume that we are working on the materials. We are approving and building the International Fusion Material Irradiation Facility and developing the technologies, the magnets, the remote handling, the heating systems, the fuel cycle, the safety, and working on the design of DEMO. DEMO stands for demonstrator, the first prototype power station which will demonstrate really putting power. If during the 20 years of building and operating ITER, we do the technology as well. Then, in 20 years from now, we can start building DEMO, and in 30 years, it will be putting out power. And then, this will just be a demonstrator, maybe a few in the world. What we really want is 10, 20, 30 fusion power stations. That will come later, around the middle of the century. This is a rather minimal program. It would be better if we had certain other devices and a more aggressive approach. And in my opinion, it would be justified. Let me deal briefly with the cost of this. People sometimes say, fusion's very expensive. Why don't we put more money in wind energy, for example? Well, I can tell you, in Europe, we are putting huge amounts in wind energy. The electricity companies are forced to buy wind energy at huge prices. In Germany, 50 euro cents a kilowatt hour is costing to get wind energy. I could make a fusion power station at that cost. So we're putting a lot of money in wind. That's the first point. The second point is the money we are putting in energy in general, and fusion in particular, is very small compared to the size of the energy market. The world market in energy, it varies with the cost of oil. But it's something like $4 or $5 trillion a year. $4 or $5 trillion. Public energy R&D, publicly funded, is 1/4% of that number. And it's less than it was in 1980. So I don't listen to people who tell me this is too expensive. Society ought to be, you can certainly spend more than 1/4% of the market on developing for a completely different market that we're going to need in 50 years' time. And we must do that. So I come to my conclusions. Fossil fuel scarce. There will be little left in the second half of this century. We don't know exactly when. Meanwhile, I think they're going to be burned. So carbon capture and storage, if possible, is essential to limit climate change. We must develop solar, and we must develop nuclear, which means fast breeders in the longer term. Thorium maybe meanwhile, and fusion, because they are the only options for replacing a large part of the world's energy that today is provided by fossil fuels. Of course, we should use the other renewables, wind, etc. And we must reduce energy use. All these things are essential, but we mustn't forget there's going to be a big gap if we only put money in wind and so on and efficiency. We must be looking at large-scale solar, fast breeder reactors, thorium reactors, and fusion. With so few options, we cannot afford not to develop fusion. Here's a quote from the Financial Times, London newspaper, just when the ITER site was agreed in 2004. Even if ITER runs well over budget, its spending level is unlikely to exceed $1 billion a year. This is a small price to pay for a reasonable chance to give the world another energy option for a time when it will no longer be possible to burn fossil fuels on the profligate, the extravagant scale of the earlier 21st century. And I'm absolutely sure that this is true. So finally, is it true, in the words of Lev Andreevich, that fusion will be ready when society needs it? Well, if all goes well, demo could be putting fusion power into the grid in 30 years. This needs adequate funding. World fusion funding is around $1.5 billion a year, compared to the world energy market of maybe $4 trillion. And it needs funding not just to make sure ITER works, but to begin the test reactor for materials and develop the technology. And it assumes we don't get a bad surprise. So it looks as if fusion could be ready, at least not for climate change. We're too late for climate change for all technologies. But it looks as, except carbon capture, it looks as if Lev Andreevich Artemovich was correct. Fusion could be ready when the fossil fuels become scarce and society will need it. Success is not 100% certain. But I am 100% certain that we must make every effort to ensure that, if possible, fusion is ready. Thank you very much.
Okay, this lecture is now open for questions. Пожалуйста, вопросы. Поднимайте руки и дождитесь, пожалуйста, когда к вам подойдут девушки и товарищи с микрофоном. Пожалуйста, вот здесь.
Где?
Thank you very much for very interesting lecture. I have a small question, because a week ago we had publication, popular now newspaper, where about ITER and its title is that ITER is good, but perhaps Americans will win the race in their laser implosion systems, or laser drop implosion systems, which are developed now. So I must know that Andrei Sakharov is also the father of this with his secret report. But what's your opinion about laser perspectives? Thank you.
Очень хороший вопрос. So the question is about what's called inertial fusion, which I didn't mention, and I didn't mention because I think we should be developing it, but I think it is much less promising. So inertial fusion uses tiny pellets of deuterium, tritium, and lithium, which are coated in some plastic. Lasers are focused on them. The plastic burns off, and the reaction compresses the material to fantastic densities, and fusion can occur. So this is like a mini H-bomb. This work is being funded by military, because these are the same. This is what I'm talking about, very, very different from thermonuclear weapons. But these are the same conditions, so these experiments, similar experiments, are done to develop nuclear weapons. Now, the development of this as a power station is maybe 1 or 2 generations behind, and it faces additional problems. Let's suppose we can get it to work.
Excuse me.
Then
I'll have to translate.
Oh, sorry, I stopped.
Ну да, я не уверен, что я все уже перескажу. Значит, есть технология, которая называется инерциальный термоядерный синтез. Это использование слоев дейтерия и трития.
Не слоев.
Нет?
Это использование дейтерия и трития, дейтерия, трития и лития, собранного в маленький объем. Значит, который заключен, скажем, в пластике, внутри пластика, значит, со всех сторон на него направляются лазеры,
Да.
так что создается большое давление и высокая температура. В результате происходит термоядерная реакция, реакция термоядерного синтеза там.
И эта технология похожа на ту, которую интересуются военные, хотя это и не совсем то, что необходимо для термоядерной бомбы.
Ну, опять не совсем. Эта технология финансируется, деятельность финансируется военными по той причине, что условия, которые при этом достигаются, близки к тем, что происходит во время взрыва термоядерной бомбы. Вот так я бы перевел.
Да, я
Ну, да.
прошу прощения.
Okay, should I continue?
Yeah.
So, supposing, first of all, we make it work. There are exactly the same problems with materials.
Предположим, что все это будет функционировать. Мы столкнемся с теми же проблемами по отношению к материалам,
But there are additional problems.
но есть и дополнительные проблемы.
To make this work, the lasers must work something like 5 times every second.
Для того, чтобы это работало, лазеры должны функционировать с частотой примерно 5 раз в секунду.
Right now, these lasers work once every few days.
В настоящий момент такие лазеры могут работать один раз в несколько дней.
In particular, the device at Livermore in the United States
Установка
can only fire 12 times in 1 year.
Установка в Ливерморе может работать 12 раз в году.
Furthermore, these pellets have to be very carefully manufactured.
Кроме того, сам рабочий объем должен быть изготовлен очень тщательным образом.
Today they cost several $1,000s for one.
В настоящий момент стоимость такого рабочего объема несколько тысяч долларов.
Okay. Needs to come down to maybe 10 cents, something like that.
А нужна стоимость в 10 центов или что-то в этом роде.
So these are not impossible,
Это не невозможно.
but they are big challenges, and the same
Но
challenge
это
of
трудно.
reliability of complex systems.
Ну и те же вызовы или те же сложности с надежностью системы.
Furthermore, lasers are rather inefficient. The power that gets into the laser beam is only maybe 1% of the power it needs. So there's an additional challenge.
Кроме того, лазеры неэффективны.
But I think we should develop it. But
Тем не менее, я думаю, что нам нужно разрабатывать эту технологию.
Окей, следующий вопрос вот там в середине. Подождите секундочку. Микрофон.
Вот хорошо, что вы мне дали возможность сейчас задать вопрос, потому что он имеет отношение вот к масштабам эксперимента. Вот вы употребили, что значит, там маленькие объемы берутся, и время как бы тоже масштабировано. А вот в том, что предлагается, имеет ли эксперимент, масштаб эксперимента имеет ли какое-нибудь значение? Я даже поясню, что я имею в виду. Взаимодействие с окружающей средой. Вот Tokamak, который в лаборатории испытывается, и Tokamak, который вот хотят построить, европейский, значит, большого масштаба, имеет ли масштаб значение для порождения новых неустойчивостей?
Tokamak, is it relevant for generating new instabilities and potentially for environmental impact?
okay. So question is about, if I understand, it's about the scale of the Tokamak, instabilities, environmental impact. Is that correct?
Я понял вопрос так, что это вопрос о том, о размере Токамака, возможных неустойчивостях и влиянии на окружающую среду.
Okay.
Inverse. The impact of environment on the work of the device, and then she refers to what happened in Switzerland at CERN.
Okay.
Why all the transformators burn?
At CERN.
Yeah.
Okay. The question of what happened in Switzerland at CERN, that's a completely different technology with completely different reasons. It's nothing to do.
Да.
It's just
Вопрос о
separate.
том, что произошло в ЦЕРНе, это совершенно другой вопрос, совершенно другие технологии, никак не связаны с тем, что здесь происходило.
The scale of the Tokamak is simply set. It has to be very big in order to generate more power, more energy than it uses.
Размер токамака должен быть очень большим просто потому, что только так можно обеспечить производство большего количества энергии, чем то, которое необходимо для его функционирования.
Okay, but it's not big. If you've been to a conventional power station, they are very big. If you go to a one.
Но если вы сравните с размерами обычной электростанции, ничего особенного в этом нет.
Impact on the environment,
Что касается влияния на окружающую среду,
bad impacts.
имеется
the radioactivity
два
in the long
фактора.
term.
Первый — радиоактивность в
But this
долгосрочной
is
перспективе.
much less of a problem than in fission.
Но это
We have
гораздо
been-
меньшая проблема, чем
We have
в
been
ядерных
living with the
станциях.
problem of fission for 50 years.
Мы имеем дело с этой проблемой в ядерных станциях уже 50 лет.
There is an additional problem, which is tritium.
Есть еще
if it
одна
escapes.
проблема — это тритий.
But the amount of tritium is very, very small.
Но то количество, которое
rather
может уйти из
easy to
установки,
prevent
очень мало
escaping.
и
Even if a
довольно
large
легко
amount
предотвратить
escapes,
утечку трития.
it will not do huge damage. But
В любом
nothing is
случае,
safe.
В любом случае, ничего плохого, то есть трудно ожидать, что что-то плохое произойдет, хотя, конечно, 100% гарантий нет.
Okay. Еще вопрос, пожалуйста. Вон вопрос сзади там. Ага.
А сколько такая штука проживет, даже если она будет построена? Сколько лет она сможет профункционировать после того, как будет построена? Я спрашиваю про ITER и про демо.
What will
Okay. So for ITER, the lifetime will be something like, after it's built, it will be operated maybe for 20 years, maybe longer, maybe 30 years.
Для ITER это время 20 или более лет после того, как он будет построен.
For power station, in the long run, if you want it to be economic, you must assume it's going to operate for something like 40 years.
Для электростанции промышленной, для того, чтобы это было экономически выгодно, такая штука должна работать лет 40 или больше.
Здравствуйте, у меня такой вопрос. Вот вы говорили, что есть некоторые проблемы с финансированием, и я хотел бы узнать, а сами нефтяные компании, ну или компании, которые используют такое сгораемое топливо, ископаемое, они не понимают, что через какое-то время, через 50 лет, через 100 лет их топливо, собственно, закончится, и их деньги тоже. Наверняка они это понимают и вкладывают деньги в перспективные проекты по энергетике. Как вы можете это прокомментировать? Спасибо.
Очень хороший вопрос. At the moment, the money is coming, government money.
В настоящий момент деньги дает только правительство.
I think we will have enough to build ITER.
Этого будет
The
достаточно
oil
для
companies
ITER.
are beginning to get interested. The
Нефть-
difficulty is capitalism.
Нефтяные компании начинают проявлять интерес, однако трудность в том,
The oil
что
companies
есть
wish
капитализм.
to make profit. They look 5 years ahead or something for profit.
Нефтяные компании рассматривают доходность на горизонте примерно 5 лет.
Here we're talking about something which commercial fusion power will come later than demos, so 40 years.
А коммерческое использование термоядерной энергии — это 40 лет,
It's
если
very
считать от этого момента.
unlikely that private money will go into things so far ahead, even if it was 100% certain, and it's not 100% certain.
Поэтому довольно трудно ожидать, что частные деньги пойдут в этот проект, в проект с горизонтом 40 лет, даже если бы была стопроцентная уверенность в успехе, а таковой нет.
The nuclear fusion reaction has 1,000 gain. The ITER and Tokamak has only 10 times, so you 100 times less. It's very low efficiency, very low. What do you think about field reverse configuration and that pinch like this machine?
Sorry, what configuration? I missed
Field reverse configuration, plasma and field reverse configuration.
What configuration?
Okay, if you don't know, it's
reverse
that.
field.
Yeah,
Okay. Okay. Do you want to translate the
and
question?
also that machine.
Okay.
I want to ask, what do you think about...
No, I understood, but maybe
Yeah.
you give the question in Russian.
Okay. Вопрос в чем, что реакция имеет выход энергии примерно в 1000 раз, больше, чем вы вкладываете. В токамаке заложено всего-навсего в 10 раз больше. То есть токамак по определению имеет очень низкую эффективность, поскольку в нем отсутствует механизм, ну такой внутренний механизм, который позволял бы это делать. Ну типа как цепная реакция в атомной бомбе. Есть другие механизмы образования плазмы, типа называется по-английски field reverse configuration, мы называем это компактные торы, где имеется механизм, внутренний механизм сжатия, достаточно эффективный для сжатия плазмы.
Okay, so the first question was about the efficiency of tokamak compared to inertial fusion, I think.
Первый вопрос — это эффективность токамака по сравнению с inertial fusion. Инерциальный термояд.
So it's important to understand that the tokamak operates continuously.
Важно понимать, что токамак будет функционировать непрерывно.
Whereas the inertial fusion is very short pulses every
В то время как
maybe 5 times a second.
инерциальный термояд будет осуществляться в пульсирующем режиме, возможно, с частотой 5 раз в секунду.
So inertial fusion needs a much higher gain.
Поэтому эффективность инерциального термояда должна быть гораздо выше.
Especially since the lasers are very, very inefficient.
В частности, потому что лазеры крайне неэффективны.
So in inertial fusion, it's absolutely necessary to have a fully self-burning, self-sustaining plasma.
Поэтому
in inertial fusion, it must be completely burning.
Поэтому при инерциальном термояде необходимо достичь полного сгорания плазмы.
In ignition, in other words, that's the word, ignition.
Зажигание.
I don't know what ignition is in Russian.
Зажигание.
Okay, ignition is vital in inertial fusion.
Тем самым зажигание — это жизненно важный момент для инерциального термояда.
In magnetic fusion, we don't even want ignition because we have better control of the plasma without ignition, and we don't need that huge.
При магнитном термояде мы вообще не нуждаемся ни в каком зажигании.
As far as the
поджиги, да.
As far as the reverse field pitch, this is in a different configuration, developed in the UK actually. We are not working on it in the UK. It's not as good as the Tokamak.
А что касается технологии reverse field, я не знаю, как это на русский переводится. Reverse field, то мы не работаем над...
Нет, в UK... В Великобритании он был придуман, этот, так сказать, подход.
Но они не
и говорит, нет, мы над ним работаем, но, говорит, это самое, он хуже, по его мнению, чем Tokamak.
Спасибо.
Ставит ли проблема создания ITER новые вопросы перед фундаментальной теоретической физикой? Или теоретически уже более-менее все ясно?
That also is a very good question.
Очень хороший
We have
вопрос.
never had a burning plasma.
У нас никогда не было горящей плазмы.
Нет. Сгорающей плазмы. Сгорающей плазмы, в которой вырабатывается энергия.
This is not, doesn't mean ignition. Burning means
Это не поджиг.
most of the heat is coming from fusion.
Горение означает, что большая часть тепла происходит от термоядерного синтеза.
It's possible that there are new physics effects.
Возможно, что имеют место новые физические эффекты.
We don't think so.
Мы так не думаем,
But we need to check on that.
но это нужно проверить.
So there could be new physics effects in ITER.
В ИТЕР могут появиться новые физические эффекты.
Вопрос еще, пожалуйста, вот здесь впереди. Сейчас микрофон.
Будьте добры, скажите, как вы относитесь к перспективе замены хотя бы в будущем трития в токамаках на дейтерий или на гелий-3?
The There is a fusion reaction which uses helium-3 and boron, and there are reactions which don't produce neutrons. But these reactions, sorry.
Имеются реакции.
There are reactions which involve boron and helium-3, which do not produce neutrons.
Имеется, значит, существуют реакции бора и гелия-3, в которых не появляются нейтроны.
This looks interesting. No radioactivity.
Это выглядит интересно, поскольку радиоактивных последствий не имеет никаких.
However, these reactions need a much higher temperature.
Но для этих реакций нужна гораздо большая температура.
It's very difficult to make deuterium and tritium. These reactions will be much harder.
Уже трудно осуществить это с дейтерием и тритием, а для упомянутых вами реакций это еще труднее.
Furthermore, there is not so much helium-3.
Не так много гелия-3 имеется.
Unless we go to the moon, and I know some people.
Ну да, если только мы не полетим на Луну, как предусматривается в частности российской космической программой. Однако это тоже очень дорого.
Also, the neutrons have an advantage. They spread the heat, so it's easier to deal with these very high heat.
Преимущество нейтронов в том, что тем самым тепловой импакт распределен по всем направлениям.
So maybe in the long run we will use such.
Возможно, в долгосрочной перспективе такие вещи будут использоваться. Но в настоящий момент целесообразно сосредоточиться на том, что и так трудно осуществимо.
Еще, пожалуйста, вопросы. Сюда, да.
I wanted to ask you about cost of electricity, your estimates, because as I understood, technology, especially material technology, is unknown, but precision of your evaluation is better than factor 10. Means, how did you evaluate? Probably it's optimistic estimate or not?
Сейчас, подождите секундочку, wait a second. Переведите, пожалуйста.
Okay.
Да, пожалуйста, сами.
Были представлены оценки стоимости электричества на стендекс. Как из доклада следует, с точностью лучше, чем 10%. Но технология, особенно материалов, неизвестна. И там может быть трудности, опять же, с упомянутой радиоактивностью трития или еще с чем-то. Поэтому какие-то предположения о цене материалов были заложены в эту оценку. Какие?
Okay, so you're asking about the reliability of the cost estimates of electricity.
Да, вы спрашиваете о надежности оценки стоимости энергии.
These estimates are the best that can be done.
Это наилучшие оценки, которые сейчас возможны.
With any future technology, maybe it's wrong a factor of 2, I don't know, but not a factor of 10, I think.
При будущем развитии технологий возможно улучшение, ну там в 2 раза, но не в 10.
So the first model, the simple model, model A.
Первая простая модель, модель А.
This is quite similar to ITER.
Она очень похожа на ITER.
Where we have quite good costings.
Где эти оценки стоимости надежны.
Remember, half of the cost is in turbines, cooling towers, things that we know.
Половина цены в охлаждении, турбинах и вообще в других вещах, о которых у нас есть хорошее представление.
So the error is diluted. If we get wrong a factor of 2 for fusion, it's only 50% for the total.
Так что ошибка реально размывается. Если половина надежно оценивается, это, соответственно, уменьшает неопределенность. Конечно, с тех пор, как мы сделали эту оценку, теперь мы уже знаем, что ITER будет стоить дороже.
So I asked the people who did the cost, hey, maybe you should revise your cost.
Поэтому я спрашивал людей, которые сделали эту оценку, может быть, вам нужно пересмотреть ее в свете того, что цена ITER больше. Их ответ был такой: мы всегда знали, что ITER будет стоить дороже. Они на самом деле использовали некий скейлинг практически...
Maybe it's not 9 cents, maybe it's 12 or 15, I don't know, but it's not $9.
Люди, которые готовили эти оценки, использовали некие скейлинговые законы, используют данные об уже работающих токамаках. Так что, может быть, это не 9, а 12 центов, скажем, но цифры такого порядка.
Okay.
Еще вопросы? Пожалуйста, вот здесь вопрос.
Скажите, пожалуйста, известно, что есть такая проблема, что высокоэнергетичные нейтроны, особенно с энергией выше 14 МФ, которые, как известно, являются релятивистскими уже, они вызывают, ведут себя буквально как слон в посудной лавке в материале. И вот, в связи с этим, как мы знаем, они вызывают каскады смещения, тепловые пики. Вот как вы считаете, какие вообще в связи с этим перспективы применения таких металлических материалов, как ОЦК стали, и возможно ли обойти эту проблему при помощи аморфизации поверхностного слоя?
Yeah. Okay. So you say that the neutrons are like an elephant, как слон. Okay.
Вы говорите, что нейтроны ведут себя как слон.
Right.
Да.
But what happens? The neutron hits an atom.
Нейтрон взаимодействует с атомом.
In the wall.
В стенке.
It pushes the atom out of its position, which pushes more atoms.
Он тем самым смещает атом из его нормального положения, и это приводит к смещению других атомов.
The neutron travels maybe 10 centimeters.
Нейтрон проходит расстояние примерно в 10 сантиметров.
Then it does it again.
Потом еще одно соударение.
And then again.
Снова и снова и снова. Так что это повторяющийся процесс.
At higher energy,
при более высокой энергии,
in fusion compared to fission,
при более высоких энергиях, которые характерны для термоядерного синтеза по сравнению с делением ядер,
the basic process is the same, but there are more steps.
Базовый процесс тот же самый, но в этом процессе больше стадий, больше этапов. Больше шагов. Да.
Therefore, we think
Поэтому мы думаем,
that with the data from fast breeder reactors in the Russian Federation,
поэтому мы думаем, что данные, которые будут получены на реакторах с быстрым размножением России,
what happens at higher energy.
Мы сможем смоделировать то, что произойдет при больших энергиях
And these
нейтронов.
data suggest that the low activation body-centered cubic steels are okay.
И информация, имеющаяся, свидетельствует о том, что низкоактивированная объемно-центрированная сталь вполне подходит для этих целей.
But it's not certain.
Это уверенность не стопроцентная.
So we need experiment.
Поэтому нужны эксперименты.
And in addition, these reactions produce helium.
И кроме того, в этих реакциях рождается гелий.
In terms of the relative to the simple damage, 100 times more helium in fusion as compared to fission.
И в процентном отношении в 100 раз больше производится гелия при термоядерном синтезе, чем при делении.
So this is a new effect.
Это новый эффект.
So we're studying theoretically, but we need experiments.
Мы изучаем его теоретически, но требуются и эксперименты. Еще раз вопрос.
Поверхностный слой становится аморфным.
Аморфизация. There was also a question on amorphization of the surface.
Yeah. I think the surface problems, that's, I don't want to get into that. Очень сложно.
Так, еще, пожалуйста, вопросы. Сейчас я видел вопрос где-то сзади. Не было. Ну ладно, пожалуйста, давайте. Sorry, just одну секундочку. Is it okay? The
sure.
question?
If it's okay with you.
It's okay with us, but how about you?
I thought my talk was all clear, but no.
All right.
Как по вашему мнению, стоит ли тратить время и усилия на исследования в области так называемого холодного термоядерного синтеза, или же это пока выглядит как очевидное шарлатанство? Спасибо.
Okay. So, actually, I was talking to Russian Newsweek before.
Я только что разговаривал с репортером российского Newsweek.
He asked me, what do I think of cold fusion?
Он спросил меня, что я думаю о холодном синтезе.
And my answer was пошлость.
Ответ был пошлость.
Ответ был пошлость.
It's science fiction.
Научная фантастика.
Еще вопрос, пожалуйста. Вот тут еще вопрос.
Вообще тут уже задали одну часть моего вопроса про холодный синтез. Но, если честно, мне бы очень интересно было послушать ваше мнение о перспективах развития этой области термоядерного синтеза далее, чем на 50 лет. Вот вы предсказали предсказали развитие этой области.
Вы имеете в виду холодный синтез?
Нет. Я имею в виду просто ваше мнение о том, что будет с этой научной областью дальше, чем 50 лет. Возможно, это сейчас научная фантастика, но все-таки интересно послушать ваше мнение. Ну, если мы все на верблюдах не будем кататься через 50 лет. Спасибо.
Okay. If we assume
Если предположим,
that we can make fusion work, commercial fusion in 50 years.
Что через 50 лет у нас будет коммерчески работающий термояд.
What role fusion will play will depend on the cost and the cost of the alternatives, solar and fast breeders.
Тогда роль термояда будет зависеть от его стоимости, в том числе относительной стоимости по отношению к солнечным и реакторам с быстрым размножением. Если вы спрашиваете, есть ли какие-нибудь ограничения по материалам, ответ нет. И эта технология термояда может развиваться очень быстро. С одним исключением.
At ITER we are using superconducting magnets which are cooled by helium.
В ITER используются сверхпроводящие магниты, охлаждаемые гелием.
The world is going to run out of helium. It's found in oil and gas fields.
В мире закончится гелий.
So in the long run we will need magnets.
Поэтому в долгосрочной перспективе нужны магниты, которые будут или охлаждаться водородом, или высокотемпературные сверхпроводники.
Be able to do this, maybe magnesium diboride magnets, but this is going to, in the very long run, this is a problem for every technology that uses superconducting
Предположительно, это достижимо
diboride.
Сейчас магнезиум диборайд, магний бор-2. Вот в магнитах, основанных на магний бор-2, возможно, это и достижимо.
It's a superconductor that works with liquid hydrogen.
Да, это сверхпроводник, который работает с водородом, при охлаждении водорода.
Еще вопрос, пожалуйста. Вот вопрос там сзади, да.
А вот скажите, пожалуйста, вот прозвучала цифра, может быть, это как-то с переводом неточность, 5 триллионов долларов. Это на всю программу, имеется в виду несколько десятков станций строительства?
Нет, это вес нефтяного рынка сегодня. Это сколько сейчас энергетического рынка, сколько сейчас, какой объем энергетического рынка в год на сегодня в мире?
Вы спрашивали о стоимости ИТЕР.
Стоимость ИТЕР, да, там понятно. А вот на несколько десятков станций сколько оценивается, как вы предполагали?
Well, Бог знает.
Бог знает.
Maybe, I don't know. When the technology is developed, new power station will cost 5 or 10 billion, something like that.
С развитием технологий станция будет стоить 5-10 миллиардов.
But they're big. They're making a lot of power.
Но они большие.
But this is a fission power station of the scale is maybe costing 4 billion or something like that.
Но в ядерных станциях цена 40 миллиардов. 4. Прошу прощения.
Так, у вас вопрос, продолжение вопроса или что-то?
Хотел спросить, а продумываются ли какие-то системы для сохранения энергии, там, основанные на сверхпроводниках, там, может быть, на каких-то соленоидах, потому что... Ну, это относительно того, что он же будет большую мощность потреблять, а, допустим, выделять большую мощность. А города работают в пиковых режимах. Например, там час пик, потребление высокое, ночное потребление низкое. Значит, нужно эту энергию как-то усреднять по времени. Соответственно, может быть, как-то на сверхпроводниках.
Okay. So the fusion power is making electricity.
Энергия термояда используется для получения электричества.
Some of that electricity is then used to heat the plasma.
Некоторая часть этого электричества используется для дальнейшего, для последующего нагрева плазмы.
And some is used to operate the superconducting magnets and other systems.
А некоторая часть используется для работы сверхпроводящих магнитов и других систем.
But when I talk about a 1.5 gigawatt power station,
но когда я говорю о 1,5 гигаваттной электростанции,
I'm considering that lithium and water are coming into the site.
Я рассматриваю ситуацию, когда литий и вода
And out of the site is 1.5 gigawatts.
на входе, а на выходе 1,5 гигаватта энергии.
And that's it. So it operates itself.
И
But
все.
it's interesting with the very primitive model, Model A,
Но интересно,
easy to build.
что в самой примитивной модели А,
The fusion power is 5 gigawatts, the fusion power.
мощность термояда 5 гигаватт.
So this is maybe producing 2 gigawatts of electricity,
Тем самым
and 500 megawatts is used to operate.
при этом получается 2 гигаватта электричества и 500 мегаватт используется для того, чтобы система работала.
The more efficient model, maybe 2.5 gigawatts of fusion power for 1.5 gigawatts electricity.
А в более совершенной модели из 2,5 гигаватт на входе получится 1,5 гигаватта электричества на выходе.
No, actually the question was different, I'm sorry. The question is, since the big cities, as an example, work as a peak or irregularly, need electricity irregularly, how would it be possible to store the energy produced?
Okay, that's a very good question too. So
Это тоже очень хороший вопрос.
you can operate at lower power in the night, for example.
Можно работать с меньшей мощностью
But
ночью.
operation costs almost nothing.
Но
So-
операционные расходы ничтожные.
So obviously people are thinking about using the electricity at night time to make hydrogen.
И поэтому люди думают над тем, чтобы использовать ночное электричество для производства водорода.
As a way of storing energy.
Как производство водорода как способе запасать энергию.
But this is similar with fission. It's cheap to operate,
Да,
expensive to
это
build.
похоже на деление, и это сравнительно дешевый процесс.
Так, еще вопросы. Вот еще, пожалуйста, вопрос. Давайте мы, наверное, еще пару вопросов и будем закругляться.
Как вы оцениваете перспективы использования других конструкций, отличных от Токамака, например, втилатора? Ведь теоретически он может работать непрерывно, в отличие от того же Токамака.
Yeah. Okay. So there are two other
Имеются
magnetic confinement devices.
две установки с магнитным удержанием, отличных от Токамака.
First, the stellarator.
Первый стелларатор.
So what was discovered by Tam and Sakharov and others,
То, что там Сахаров и другие обнаружили,
you need a magnetic field which is helical.
вам нужно геликоидальное магнитное поле.
So they suggested you make this with a solenoid and an electric current.
И они предложили
But at the
генерировать такое поле при помощи соленоида и тока, пропущенного через тор.
But at the same time, Lyman Spitzer at Princeton
В то же время Лайнен Спицер в Принстоне
suggested to make a helical field from outside without a current by very complicated magnets.
предложил создавать такое геликоидальное поле внешними устройствами, весьма сложными, внешними по отношению к объему рабочему.
Okay, this is a stellarator.
Это стелларатор.
It's a very beautiful idea.
Это прекрасная идея.
But it's a theorist's idea.
Но это теоретическая идея.
It's very difficult to build.
Эту установку очень трудно построить. Очень сложная, очень дорогая.
Difficult to get the blanket.
И очень трудно оболочку В принципе, у стелларатора есть преимущество, поскольку ток в токамаке флуктуирует. А эти флуктуации могут приводить к нестабильностям, генерации нестабильности в плазме. Теоретически стелларатор очень хорош. Но если токамак будет работать, то это будет дешевле и проще. Поэтому стелларатор нужно развивать и надеяться, что он не понадобится. Еще одна разновидность — это так называемый сферический токамак. Это тоже токамак. Он больше похож на яблоко, а не на бублик. И лидерами в этих исследованиях являются исследователи в Великобритании, Принстоне и Санкт-Петербурге.
There is a question in the written form. Ваш ИТЕР предполагает температурное сталкивание атомов дейтерия и третий при помощи температуры. Думают ли теоретики о применении резонансного метода, как это делал Никола Тесла? ITER assumes that the collisions between deuterium and tritium would occur because of temperature. Do theorists consider using resonance method as was done by Nikola Tesla? I can't comment.
There have been other ideas, such as resonant methods, but none of them seem able to produce the right conditions in a sustained way.
Выдвигалось много идей, но ни с одной из этих идей не удавалось добиться условий для надежного функционирования процесса.
Ну что же, давайте мы поблагодарим нашего гостя сегодня. Thank you very much. It was very interesting, and I'm sure we have a lot of thoughts about that. Спасибо большое всем.